For today's lesson, we're going to continue with mass-mole particle conversions. So you will need periodic table, the periodic table of ions, your polyatomic ion chart, and your formula mass assignment and your mass-mole particle assignment. We're going to review the answers to those two assignments. For those of you who had trouble with the DOA today, it is probably because you did not have the correct formula for the manganese Roman numeral 2 nitrate. So if that's the case, I suggest you review the videos on formulas and nomenclature. You might want to start out with the formulas and nomenclature roundup video. It's imperative that you know how to write the proper formulas in order to be able to get the correct formula mass in order to be able to do mass mole conversions properly. So today we're going to start out with this chart. And for this chart, we have the name of our substance. We're going to write the formula of our substance. And then we're going to state what the representative particle for that substance is. So the representative particle is the smallest particle you can have of that substance. So the choices would be an atom, a molecule, or a formula unit. So what I would like you to do is to pause the video, fill out the chart, and then when you're finished, come back and check your answers. And I really want you to do that. I really want you to pause the video, because just watching the video without trying to do the work, well, it's better than nothing. But to really learn, you need to be active, and sometimes you have to struggle. And that's not a bad thing. Struggling is a good thing. It helps you to learn. So go ahead, pause the video, figure out your formulas, and say what the representative particles are. Okay, so hopefully you're back from doing the work. So our first substance is sodium hydroxide. So sodium, we look at our first element, that's the most important thing. Sodium is to the left of the staircase. So that means we have an ionic compound. So to get the formula, the sodium ion has a +1 charge, sodium's in group 1, and then hydroxide is a polyatomic ion. From your polyatomic ion chart, it is OH with a -1 charge. So we cross our charges, 1 and 1, and then we rewrite. And we don't have to include ones, and if 1 is outside the parentheses, we don't have to include the parentheses. So our formula is NaOH. Now, what is the representative particle of NaOH? Well, we need to identify what type of compound sodium hydroxide is. When we have a metal, and here we have a polyatomic anion, this means we have an ionic compound. The smallest particle that we can have is called the formula unit. So a formula unit of sodium hydroxide would have 1 sodium ion and 1 hydroxide polyatomic ion. The definition of formula unit is the lowest whole number ratio of ions in the compound. All right, let's go to phosphorus trichloride. Again, most important thing, look at where this first element is on the periodic table. Phosphorus is to the right of the staircase. And we can see that we're using the prefix system here because of this tri. So for our formula, phosphorus is P. There's only one of them. We don't put the mono in front of the first element if there's only one atom. And then chloride means we have Cl. Tri means we have 3 of them. So our formula PCl3. So what is our representative particle? Well, what type of compound is PCl3? It starts with an element to the right of the staircase. So this is a covalent compound. So our smallest unit is a molecule. So our ionic compound, the smallest unit is the formula unit. Our covalent compound, the smallest particle, is the molecule. All right, our next substance is lead. All right, well, lead, that's just Pb. And the smallest particle of lead that you can have is an atom of lead. Oxygen gas. So if we have some oxygen gas, like we have oxygen gas in our atmosphere, we have O2 for our formula. Oxygen is one of the Hofbrinkel elements. So our representative particle then is a molecule. Our Hofbrinkels are covalently bonded. So the smallest particle is a molecule of O2. And then our last one, zirconium, Roman numeral 4, sulfate. So zirconium, it is to the left of the staircase. It is in the D block of the periodic table. And we have a Roman numeral here indicating the charge of our zirconium ion. So Zr, Roman numeral 4, means we have a 4 plus ion. Sulfate, Ate, indicates we have a polyatomic ion. We check our chart. Sulfate is SO4 with a 2- charge. We cross the charges, and then we check the numbers that we crossed, and we reduce them to lowest whole number ratio. So 2 to 4 goes 1 to 2. Now we rewrite it, Zr parentheses SO4 parentheses 2. For the particle, we have to identify what type of compound this is. When it begins with a metal ion, polyatomic ion, it's an ionic compound. The smallest unit is called the formula unit. So it's important to know what type of particles make up our substance. All right, so the next thing we're going to do is we're going to review the answers to the formula mass worksheet. So that's the one that looks like this, because I saw that some students did not get all of these correct, and in almost all the instances that was because they did not have the correct formula. So sodium bicarbonate. Sodium is Na+1. Bicarbonate, this whole thing is a polyatomic ion. It's on your polyatomic ion chart. It is HCO3 with a -1 charge. Cross 1 and 1, our formula is NaHCO3. Now we can figure out the formula mass from the periodic table. So I have 1 sodium atom, 1 hydrogen, 1 carbon, 3 oxygens. As indicated here, these values are from the periodic table, and then we add them up. This is 3 times 16, add them up. Your answer is 84.01 atomic mass units. That is the mass of 1 formula unit of sodium bicarbonate. This number is also the number of grams in 1 mole of sodium bicarbonate. All right, over here, arsenic tribromide. Look at the first element. Arsenic is to the right of the staircase. Prefix system here. We don't put in charges, we don't cross them, we don't reduce to lowest whole number ratio. We just look at the formula, we look at the name to tell us the formula. So I have 1 arsenic, tri means I have 3 bromines. So our formula AsBr3, 1 arsenic, 3 bromines. Be careful with arsenic. Its formula is not Ar, its formula is As. Ar is argon. So we have to get the right number from the periodic table. So arsenic is 74.92, 3 bromines, we add them all up, and we get 314.62 atomic mass units for every 1 molecule of AsBr3. We could also say 314.62 grams for 1 mole of AsBr3. All right, let's look at our next one. So here we have a sample of nitrogen gas. we have to look out for those Hofbrinkel elements. Nitrogen is a Hofbrinkel. So the nitrogen in our atmosphere is composed of nitrogen molecules, two nitrogen atoms covalently bonded. So we just take 2 times the average atomic mass of nitrogen from the periodic table, and we get 28.02 atomic mass units for every 1 molecule of N2, or that number of grams for 1 mole of N2. Iron Roman numeral 2 phosphite. So it's very important. Every single letter is so important. Phosphite is different from phosphate, which is different from phosphide. So be very careful with going from the name to your formula. So iron is Fe. Roman numeral 2 means this iron has a 2+ charge. Phosphite from your chart is PO3 with a 3- charge. Cross them, and our formula then is Fe3 parentheses PO3 parentheses 2. Now that we have the correct formula, we can go ahead and figure out our formula mass. We have 3 irons, 2 phosphoruses, because 2 times 1 is 2, and then for oxygen, 2 times 3 is 6, so we have a total of 6 oxygen atoms, and our formula mass, 356.46 atomic mass units. Okay, our next one is for table sugar, and I gave you the formula for that because we're not doing the naming for these type of compounds, but the name of this is sucrose. All right, so we have 12 carbons, 22 hydrogens, 11 oxygens. Get our values from the periodic table, do the math, add them all up, and we should have 342.30 atomic mass units. And for this, we're just taking it to 2 decimal places. Potassium chloride, ionic compound, begins with a metal, K+. Chlorine is an ion, is Cl-. Cross our charges, our formula is KCl. Get our values from the periodic table, add them up. Our answer is 74.55 atomic mass units. And then ammonium thiosulfate. So here we have an ionic compound composed of a polyatomic cation and a polyatomic anion. So ammonium is NH4 with a +1 charge. Thiosulfate is S2O3 with a 2- charge. Cross your charges, and we get parentheses, NH4 parentheses 2, S2O3. The NH4 must have parentheses around it because it has a subscript of 2 outside. The S2O3 does not get parentheses because its subscript is a 1. So now we have to count up our atoms. So 2 nitrogens, 2 times 4, 8 hydrogens, 2 sulfurs, 3 oxygens. Get our values from the periodic table, add them all up, and you should get 148.20 atomic mass units for 1 formula unit of ammonium thiosulfate. And then our last one, sulfur hexafluoride. So sulfur is to the right of the staircase. This is a covalent compound. Its representative particle would be a molecule. So we have 1 sulfur. Hexa is the prefix for 6. So we have 6 fluorine atoms in our molecule. 1 sulfur, 6 fluorines, get the values from the periodic table, add them up, 146.06 atomic mass units for 1 molecule of SF6. Okay, so now let's review the answers to your mass mole particle worksheet that you had. All right, so number 1 says to calculate the number of moles in 10.00 grams of zinc phosphate. So when we have moles in grams, that means we're going to need molar mass. To be able to figure out the molar mass, we have to have the correct formula for zinc phosphate. So zinc is part of the slide. Zinc always has a charge of 2+ when it is in a compound. Phosphate is PO4 with a 3- charge. Cross our charges, look at 3 to 2, that is a lowest whole number ratio. So our formula, Zn3 parentheses PO4 parentheses 2. Now that we have the correct formula, over here I've done the molar mass. I have 3 zincs, 2 phosphorus, 8 oxygens, which gives me a total of 386.08. Now, because I'm doing molar mass, I want to think of this in terms of grams per mole. I could say the formula mass is 386.08 atomic mass units, and that would be for 1 formula unit of zinc phosphate, but I'm doing grams and moles, so it is grams in 1 mole. So now I can do the dimensional analysis. So I set my X is what I'm looking for. I'm looking for the number of moles. So X moles of zinc phosphate equals, set it equal to the quantity of interest. I'm interested in 10 grams, equals 10.00 grams of zinc phosphate. And it's really important. Don't forget these zeros. These zeros have significant digits. So don't forget that. It's not 10, it's 10.00. Times. Now we do our conversion factor. And we see that we need to flip this because I need grams to be in the denominator to cancel out the grams that are over here. So I cancel them out, do the math, and pay attention to your sig figs. This has 4 sig figs. Remember, when you have a decimal point, you go to the end of the number. This has 5 sig figs, so my answer must have 4 sig figs. So 0.02590 moles of zinc phosphate. So you have to have that 0 at the end. Don't forget to put that to show 4 sig figs. When we're doing sig figs, remember, we never start counting until we hit the first non-zero number. So 1, 2, 3, 4 sig figs are in that number. And all your answers should have the number, the unit, and the formula. Okay, so our next question here is to determine the number of grams in 3.75 moles of phosphorus pentabromide. Again, we have grams and moles in our question, so we need to get a molar mass. We need to get the formula. So this is a covalent compound. Phosphorus is to the right of the staircase, and our name shows the prefix system. So we have 1 phosphorus atom, 5 bromine atoms, PBr5. Do your formula mass calculation, which is the same as molar mass. 1 phosphorus, 5 bromines. Get your values from the periodic table. And I got 430.47, and that is the grams in 1 mole for PBr5. Now we do the dimensional analysis. X grams of PBr5 equals our quantity of interest, 3.75 moles of PBr5, times. This time we're going to use the conversion factor just like it is because we need to cancel out moles. So I put 1 mole of PBr5 on the bottom in the denominator and the 430.47 grams in the numerator. Moles, cancel moles, then I do my math, and sig figs. 3.75 has 3 sig figs. This has 5, so my answer can only have 3 sig figs. So your calculator is going to say 1614 point something something. We need to show that this number is in the thousands. So to show 3 sig figs, I can't just write 161 because it's not around 100 grams, it's around 1,000. So 1610 grams is the proper answer. If you wrote 1614, you would show 4 sig figs. That's too many. We can only show 3. So we need that 0 as a placeholder. Do not put a decimal point because the rule for sig figs is when there is no decimal point, you stop counting when the rest of the digits are zeros. So 1, 2, 3, we stop counting, 3 sig figs for that answer. And note, I have the number, the unit, and the formula. All right, for number 3, now we want to know how many molecules of carbon dioxide are in 18.2 moles of carbon dioxide. So now, we don't have grams anywhere in this question. So we do not need to calculate molar mass. You can calculate it, but you're not going to need it. So why bother? to go from molecules to moles, that's when we use Avogadro's number. Avogadro's number is the number of particles for 1 mole, which is 6.022 times 10 to the 23rd. So our formula, we need to write that though. Carbon dioxide, carbon is to the right of the staircase. This is a covalent compound, prefix system, CO2. So X molecules of CO2 equals 18.2 moles of CO2, or quantity of interest, times our Avogadro's number conversion factor. So because the smallest particle, the representative particle of CO2 is the molecule, we use molecule in our Avogadro's number conversion factor. 6.022 times 10 to the 23rd molecules of CO2 are in 1 mole of CO2. And our answer then, 3 sig figs 4, so 3 sig figs 1.08 times 10 to the 25th molecules of CO2. So when you're reading the answer from your calculator, remember to go all the way to the right to check for an exponent. So times 10 to the 25th. All right, and number 4, what is the mass of a 7.4 mole sample of hydrogen gas? Okay, so here again we have mass and mole, so yeah, we need to do a molar mass calculation. Our formula, hydrogen, is a Hofbrinkel. If you have some hydrogen gas in a tank of gas, you will have H2 molecules, hydrogen covalently bonded to hydrogen. So for our molar mass, we have 2 hydrogens from the periodic table. Each hydrogen is 1.008, so our molar mass is 2.016 grams per mole. Now, when we have some of our masses with 2 decimal places and some with 3, I said just go to 2, but since we only have hydrogen, I'm just going to keep that whole thing, 2.016. Now we do our question. X grams of H2 equals 7.4 moles of H2. We have to use our conversion factor just like it is. We need moles to cancel moles. So we have the 2.016 grams in the numerator. That cancels. Do the math. 2 sig figs, 4 sig figs. Our answer gets 2. So our final answer, 15 grams of H2. Number, unit, formula. Okay, let's look at our next problem that we had on our worksheet. All right, if there are 5.1 times 10 to the 24th formula units of magnesium oxide in a sample, how many grams is in the sample? All right, so we have grams, we have a counting unit. That means we're going to need molar mass. So we need our formula of magnesium oxide. Magnesium's to the left of the staircase. It's an ionic compound. Magnesium is a 2+ ion. Oxygen is a 2- ion. When we cross, we get 2 to 2. That reduces to 1 to 1. So our formula is MgO. Do the molar mass calculation. 1 magnesium, 1 oxygen, and we get 40.30 grams in 1 mole for our compound. Now we do the dimensional analysis. X grams of magnesium oxide equals our quantity of interest, 5.10 times 10 to the 24th formula units of magnesium oxide. Because we're starting with formula units, we need to cancel them out. So we use Avogadro's number conversion factor. A representative particle is the formula unit. So there are 6.022 times 10 to the 23rd formula units of magnesium oxide in 1 mole of magnesium oxide. So our Avogadro's number conversion factor depends on the representative particle for our substance. That cancels out the formula units of magnesium oxide. Now we still need another conversion factor because remember, the units on the right have to cancel out until we get to the units that we're looking for on the left. So formula units cancel out. Now we have moles, so now we use the molar mass conversion factor. We need moles in the denominator so they can cancel out. So let's see, we'll just cross these out. That crosses out, that crosses out, that crosses out. Everything crosses out except for grams of MgO. Do the math, this divided by this times that, and you should get 341 grams of magnesium oxide. If you got a huge exponent, like times 10 to the 47th or something, put your Avogadro's number in parentheses because your calculator is multiplying. You need to tell your calculator, divide by this whole thing. So that's what you need to do if you did not get that correct answer. If you got a big exponent, you should not get an exponent. You could get it 3.41 times 10 to the second, but if you have a huge exponent, that's probably your problem. All right, let's look at our last one. How many molecules are in a 100-gram sample of sulfur trioxide? So again, we need our formula. Sulfur is to the right of the staircase. This is a prefix system. This is a covalent compound with a representative particle of a molecule, so SO3. Do the molar mass, and we get 80.06 grams in 1 mole. Set up our dimensional analysis. X molecules of SO3 equals 100.0 grams of SO3. We have to cancel out the grams, so that means we use our molar mass conversion factor. We have grams of SO3. We need grams of SO3 to be on the denominator, so we got to flip that. And then we can cancel out the grams of SO3. Now we have moles of SO3. Now we use Avogadro's number conversion factor. Here, the 6.022 times 10 to the 23rd is the molecules in 1 mole. In our previous problem, it was 6.022 times 10 to the 23rd formula units because our previous problem had an ionic compound. This problem has a covalent compound and the representative particles are different. When we do the math, we get 7.522 times 10 to the 23rd molecules of SO3. I use 4 sig figs because my data has 4 sig figs, my Avogadro's number has 4 sig figs, that has 4 sig figs. Don't forget to write your 10 to the 23rd because that is a huge number of molecules that we get with that amount of grams. All right, number 7, convert 25.5 grams of gold to moles of gold. So our formula of gold is just Au. So our representative particle here would just be an atom of gold. So our molar mass, we just get that right from the periodic table, and you don't have to do all that. You can just write 196.97 grams in 1 mole. X moles of Au equals 25.5 grams of Au. So we need to cancel out the grams. So grams needs to be in the denominator. So 1 mole in the numerator, 196.97 grams in the denominator. Cancel, cancel, do the math, 3 sig figs. Our answer is 0.129 moles of Au. And then our last problem. How many formula units of potassium sulfate are in 1.6 moles of potassium sulfate? So we get our formula. Potassium is to the left of the staircase. This is an ionic compound. The smallest unit is a formula unit. So potassium is in group 1, it's a +1. Sulfate, that's a polyatomic on your polyatomic ion chart. So we have F, so our formula is SO4 with a 2- charge. Cross our charges to the outside of the parentheses. Our formula is K2SO4. Now, you can see that I did a molar mass calculation. Well, that's because I didn't read the problem and analyze it. I just said, okay, I have potassium sulfate, let me do the molar mass. Do I need it? No, I don't need the molar mass. I have moles and formula units. Moles are a way to count. Formula units are a way to count. There's no grams anywhere, so I don't need it. I did it, but I don't need it, so I wasted my time. All right, now we do our dimensional analysis. X formula units of K2SO4 equals 1.6 moles of K2SO4 times. All I need is Avogadro's number conversion factor. Because I have an ionic compound beginning with a metal, that means my representative particle is the formula unit. So 6.022 times 10 to the 23rd formula units of potassium sulfate are in 1 mole of potassium sulfate. Moles, cancel moles. My unit is formula units, potassium sulfate. Do the math. 2 sig figs, 9.6 times 10 to the 23rd formula units of K2SO4 is my answer. All right, oh gosh, I can see we're at 30 minutes. So I am going to give you an assignment today, just like the one I went over, doing mass mole particle conversions. You really want to be good at this. This is one of the essential skills to be able to have to go on in chemistry. I can't even tell you how important this is. So that's why I did this review video, and I'm giving you more practice. All right, that's it.